This is our fourth video on light waves, and in this video we will look more closely at the questions related to the double slit experiment. I did derive the formula in the previous video, but I'm gonna go over it again in this video so you understand how we're gonna use this formula. So let's look at the formulas and the questions related to the double slit experiment. In this picture you see how the light waves are passing through two slits and they interfere with each other. So the picture that shows you here shows the waves interfere with each other, and when they cause the darker fringes where the waves cancel each other, and lighter fringes where the waves constructively interfere with each other and increase the amplitude. And then the result of this interference you see in the black picture, the last one, and here you see the red light. For the blue light, these dots would be even closer to each other because the blue light has shorter wavelength and higher frequency. The red lights, the distance between the fringes will be farther away. They will be more apart from each other than the blue light. And so the red light has the longest wavelength and the blue one, or the purple, has the shortest wavelength. So back to how we derive the formula. So in the previous video I mentioned to you, if this is L, the distance between the double slit and or two slits and the screen, and the first fringe, the bright fringe, appears the distance y away from the center, then from this blue triangle, maybe I'll do it in blue, right, everything in blue. So in blue triangle you have tangent theta is equal to the opposite over the adjacent, which is L. And then in the yellow triangle you have also very small angle because this bright fringe, I'm going to do it in red, appears only when the wavelength that travels shorter distance is shorter by the amount of wavelengths within this triangle. So this part needs to be number of the wavelengths longer than the shorter path to make these two equal lengths. So if this is m times lambda, where m is 1 or 2 or 3 or 4 number of wavelengths, then you will get constructive interference. They will arrive at the same phase and hit the screen at the same phase and cause the constructive interference. So when you look at this yellow triangle, because the distance d between the little scratches where the slits are is in milli or micrometers distance, and the wavelength of the visible light is in nanometers. So when you have m times lambda, m is number of the wavelengths, but lambda is very small in nanometers, then the angle that is created right here is also very small. So if I'm gonna write sine of theta, that will be m lambda divided by the distance. And from the previous video I told you to compare sine and tangent of 1 degree, because this angle and this angle are both very small. So if I say it's 0.5 degrees or 1 degrees or even 2 degrees, to use your calculator and compare sine of 1 degrees and tangent of 1 degrees, or sine of 2 degrees and tangent of 2 degrees, and you will see that these two numbers are equal to each other. So for Young's double slit formula, we have, because this for small angles is equal to this, then I can write that y over L is equal to m lambda over d. So this would be my formula for the double slit experiment. And now we're going to use the problems to see how we can use this formula to solve problems. So here's the first question. They say that the screen is separated from the double slit source by 1.2 meters. The distance between the two slits is given 0.03 millimeters, and the second order bright fringe, where m is equal to 2, is measured to be 4.5 centimeters. From the center line, determine the wavelength of the light and the distance between the adjacent bright fringes. So at first I'm going to write down everything that is given so I know my calculations and which formula to plug in into my formula. So I have to write everything that is given first. So here what is given, and then from the double slit experiment I have the y over d, y over the distance, let's call it L, is equal to m lambda over d. So the information that given is the second fringe 4.5 centimeters. So y is given 4.5 centimeters. Centi is 10 to the negative 2. The distance to the screen from the double slit is 1.2 meters. It is the second fringe, so m is 2. And the wavelength I am looking for, that's the one that they asked me to find. And the distance between the two slits is 0.03 milli, 10 to the negative 3. So from here I can calculate that wavelength is given, or wavelength is equal to 562.5 nanometers. If I want to find the distance y for m is equal to 1, because I have for the second one but not for the first one, so I'm going to use this formula to calculate the distance to the first one, and m is going to be 1. So the distance to the first bright fringe is going to be this formula, m is 1, and I can plug in my numbers right away. So this is 1.2. Then lambda I just found is 562.5 nanometers divided by the distance, which is 0.03 millimeters. So here I get that the distance to the first bright fringe is equal to 2.25 centimeters. So they ask you the distance between the adjacent bright fringes. So delta y is equal to 4.5 centimeters minus 2.25 centimeters. That's going to be 2.25 centimeters. And that makes sense that it is 1/2 of the distance, and it's always going to be 1/2 and then another half added to 4.5 is going to be the next one, and another 2.25 added to the next one, and so on. So the distance between them is going to be 2.25 between all of them. In this next question, they say for the experimental setup, we have been studying, assume that the distance is 1.5 millimeters between the fringes, and the distance to the screen is 6 meters, and that the light used as a wavelength of 589 nanometers. So how far above the center will be the first intensity maximum appear? Go ahead and pause the video and try to solve this on your own, because I think you just have to plug in into the formula to do this calculation. So go ahead and try to solve every single one of them on your own, and then check your answers with me, because I'm going to just show you calculations right now. So pause it, and I will see you back in a bit. So I hope you tried to solve this on your own at first. So for A, you see I use Young's double slit experiment formula, and I calculated that the distance between the center and the first fringe, bright fringe, is 2.36 millimeters. and then they ask you how far below the center of the screen is the third dark fringe. So I calculated that the first dark fringe is going to be the distance of 1.18 millimeters from the center, and if I want the third dark fringe, I have to times it by 3, and that will give me 3.54 millimeters. And so the third one is 3.54 millimeters distance from the center. And then for the last one, they ask you what would happen to the interference pattern if the slits were moved closer to each other. So I looked at this formula and I want to see the relationship between the Y and D. So because D, they said, is going to get closer to each other, the distance between is smaller. So when D is increasing, Y is going to be, when D is decreasing, Y is going to be increasing. So the distance between the fringes is going to increase as D gets smaller, the distance between the slits. This question is related to the Snell's law. So it says the beam of light in air is incident upon a piece of glass striking the surface at an angle of 30 degrees. So that is not the incident angle. So if this is the glass and here is the normal, then the angle is one that they're talking about is the one 30 degrees here, but I need this angle. So this angle is actually 60 degrees. And then this will be the refracted angle. So I'm looking for this angle, the angle of refraction, and angle of reflection. The reflection angle is going to be the same 60 degrees. So that's the law. So it's 60 degrees. Angle of refraction, angle of reflection is equal to the incident angle. And then for the Snell's law, I have n1 sine theta 1 is equal to n2 sine theta 2, and this is theta 2. So I have air is 1, index of refraction, sine of 60 degrees is equal to, for the glass we have 1.5, and sine of theta 2. So theta 2 is equal to arc sine, or inverse sine of sine 60 divided by 1.5. And that will give me sine 2, theta 2 is equal to 35 degrees. In this question, they say light consisting of red and the wavelength is 640 nanometers in vacuum, and blue for 40 nanometers in vacuum. So you see the blue one has shorter wavelength as compared to the red one. Is incident upon a double slit with a spacing of 4.10 to the negative fifth meters. A screen is located 2 meters behind the slit. Determine the distance on the screen between the first order red maximum and the first order blue maximum. So I'm going to calculate the first order red and first order blue, and then I'm going to subtract both of them, subtract their lengths. So here I did the calculations for the red one and the blue one using the Young's double slit experiment formula. And I found that the difference between them, change my colors, so it equals to 10 millimeters or 1 centimeter. In this picture, you see the fish in the water is seen by an observer. The effect that is caused by the refraction at the surface of the water causes the apparent depth, not the real depth, distance, to be closer to the surface of the water than the real distance would be. So every time we look down into the pool down in the water, it looks not as deep as in reality it is. Let's look at the example how we derive the formula of the apparent height or depth depending on the on the angle of refraction and the index of refraction. So starting with the Snell's law, we can write as n1 is our water, so it's going to be n1 sine theta 1, so that's the index of the incident angle, so this would be theta 1, equals to n2 and sine theta 2, and that is our refracted angle when it comes into the air. Then, because we know that the air n2 is equal to 1, and this always in the same case where it is like the liquid or water and the air, so I can write that n1 is equal to sine theta 2 divided by sine theta 1. And because for small angles that we talked when we did the thin film, the experiment or the effect of the thin film, so we talked about the sine of the angle is equal to the tangent of the angle when it is small angles. So we could rewrite as n1 is equal to tangent theta 2 over tangent theta 1. And to use the tangent part, I will make this line a little bit longer, so I made it in purple, so where theta 2 is, and that is also theta 2. And because this angle is theta 1, this angle is also theta 1. So these two green angles, they are theta 1s, and two purple angles, so I'm going to make this purple and this purple, so these two are theta 2, so this is theta 2. If I call this distance x and this is h of the image and this is h of an object, then I will have, instead of tangent, so let's write tangent of theta 2 is equal to the opposite, which is x, over the adjacent, which is hi, and tangent of theta 1 is equal to, so for theta 1 I have to look at this triangle that I'm drawing right now, the dark one, and so that will give you x over h of where the object it really is. So then now if I plug it into my equation, I have n1 is equal to theta 2 is x over hi divided by x over ho. So n1 is equal to ho over hi. So we have just derived the formula of the relationship between the index of refraction and the apparent height of the object. So hi, this is where the image of the object appears. So this is where the image of the object of the fish would appear, and this is where the fish is in reality. So point P is where the fish is, but point Q is where the fish appears to be. So maybe I'll just make it to look like a fish. And the formula would be the h of the object divided by the h of the image. And this is what we have in our lessons. So n of the water is equal to d of the object over distance to the image, one of the formulas. And if we didn't have air, which we chose to be 1, then the formula would be the one that you see on the right. So that would be the formula that you need to know. And also what's good to know is that this formula is not given on AP exam, but this type of questions may appear on AP exam, so you need to know how to derive it. So if you need to watch the derivation of this formula one more time, go ahead and derive it, and I think I can also place for you a picture here that you can stop and pause and look at it, how to derive it. So let me find it and post it here. So here I found for you the derived formula if you want to pause and look at it a little bit longer to see how what steps I went through when I explained this formula in the video. So go ahead and pause it and look at it, and I will continue with solving problems involving this concept. So in this question they say a fisherman drops a flashlight into a lake that is 10 meters deep. The flashlight sinks to the bottom of its emerging light beam is directed almost vertically upward toward the surface of the lake, making a small angle θ1 with a normal. How deep will the flashlight appear to be to the fisherman? And use the fact that tangent theta is almost equal to the sine theta if theta is small, and index of refraction of air is 1 and index of refraction for water is 133. So here I drew a picture for you where the flight is at the bottom of the lake, and then you have the angle of incidence θ1, and this angle of incidence θ1 is the same angle as this one, and then you have angle of refraction is θ2, and θ2 is the same as this angle. So I can do again Snell's law. So I have on AP exam you have to derive the formulas. Memorizing formulas doesn't help because you get points for every step that you do. So only if you have right answer you get 1 point out of 5 possible. So you have to write every single step to solve this problem. So I'm gonna say n1 sine θ1 is equal to n2 sine θ2. So n1 is given, n2 is given. Sine theta is, because they say it's very small angle, so I can replace it with tangent. So I will say n1 tangent θ1 is equal to n2 tangent θ2. So for tangent, if I look at this big triangle, so I'm gonna make all this big triangle, this is h, and I'm gonna call this length x. So if this is x and this is θ1, then I have the tangent is x over the capital H. So I have n1 and then I have x over the capital H. And then I have n2, and I'm going to draw the little triangle right here. So this is θ2. This is still x, and this is the lowercase h where the image appears. So that is for tangent, I have x over the lowercase h, where the image appears. Then x and x can be cancelled. And what I have now is n1 over h is equal to n2 over h. And we're looking for where image is appearing, so h is equal to h and 2 divided by n1. So the depth of the lake is 10 meters, and 2 is 131, so I made a mistake here when I plugged it in. So n2 is 1, it's the air, and n1 is 133. So n2 is air 1, and n1 is 1.33. So the apparent height where the flashlight appears is equal to 7.52 meters. In this question, they say a scuba diver training in a pool looks at his instructor as shown in the figure. What angle does the ray from the instructor's face make with the perpendicular to the water at the point where the ray enters? And the angle between the ray and the water and the perpendicular to the water is 25 degrees. So the angle they ask us to find is this angle, so I'm gonna call it θ1. This is n1, this is n2, and we know the distance and where the diver appears to be. They give you the distance to the diver, where he appears to be is 2 meters, and how far from where the instructor looks at we have that distance as well, 2 meters. So we have this distance, and we have distance where the scuba diver appears to be 2 meters. And we have the index of the angle of refraction is 25 degrees. So this angle 25 degrees. So theta 2 is 25 degrees. Okay, so that is the information that is given. So again, I can use this information. I'm gonna look at this triangle, and this is also theta, and I will look at this triangle, the yellow one. So right here, the yellow triangle is the one where the scuba diver appears. So that's the right angle triangle as well, because I have those two links, 2 meters and 2 meters. I don't know this angle, but that angle is the same as this angle. So this is 90, and this angle is the one that we're looking for, and this is also the one that we're looking for. And we do not know this angle. So what we can do is we can find theta 1 angle by using the Snell's law. Let's try. So I have n1 is 1, sine theta 1 I'm looking for, theta 1, and 2 is 133 for water, and sine theta 2 is 25 degrees. So theta 1 is equal to arc sine, or inverse sine of 1.33 sine of 25 degrees. So theta 1 is equal to 34.2 degrees. I think I'm gonna stop our video on light waves 4. At this point, I have very limited time to finish this video, only 2-3 minutes before the time runs out. So there's going to be more questions solved on flat refracting surfaces in Snell's law and double-slit experiment, and maybe even flat thin film problems in the next question. And I will say thank you for watching this video, and I'll see you in the next one.